All right, I know I said there were two extra problems. There's actually only one extra problem, but still, figured better to go ahead and do it anyway. So, for this one, it's kind of the opposite of the last one we did in class. So, if you notice, this one is actually well, it has bounds of integration, so we have to deal with those. But it's also exponentials. One thing to be aware of, remember we said if you have something, it's like if I have x to the a raised to the b, it's the same as x to the a times b. So for here, when I have the natural log of 3/4, or the integral from the natural log of 3/4 to the natural log of 4/3, I can rewrite this. This is e to the t still on top. But remember, this is the square root of 1 plus e to the 2t is the same as e to the t squared. This is also to the third. So one thing we're going to do to make this easier at the start is we're going to let u be equal to e to the t. And if we do that, we get that du is e to the t dt. And then if I want to evaluate the upper bounds, ln of e to the ln of 4/3, since they're inverses, it's just going to be 4/3. And then ln of 3/4 is just 3/4. So this means we don't have to go back to natural logs at the very end of the problem. But now this gives us the integral from 3/4 to 4/3 of 1, because we'll grab the e to the t dt and replace it with du, over the square root of 1 plus u squared cubed. That's all under square root. And that's du. So the last one we had to do a u substitution after doing the trig substitution. This time we're doing the u substitution before the trig substitution. So if we draw our triangle, remember I got my theta, and it's a right triangle. If I try and set this up as a equals the square root of 1 plus u squared, well, that works out immediately because I get a squared equals 1 plus u squared. So I know that this has to be the hypotenuse. So in this one, I get to get away almost immediately with sorry. I get to get away with using the hypotenuse and not having to do anything like weird or have to go, okay, well, where's the square root go? Now, though, I have to come to the thing of, do I need to use sine, cosine, or not cosine? I keep wanting to say those just because they're one follows the other. Do I need sine, tangent, or secant? Well, if we look at this one, we want to try and avoid anything that uses the hypotenuse, because again, you don't want to introduce anything that you don't have to with the square root of 1 plus u squared. The whole point of doing a trig substitution is trying to escape the square root of this weird thing. So in order to avoid that, let's use tangent. Looks like it's going to pop up the most because tangent's going to avoid this guy, the square root of 1 plus u squared. And if tangent's going to be opposite over adjacent, let's make u be equal to this opposite side, and let's make 1 be our tangent. It just works out pretty well there. So that means that tangent of theta is going to equal u over 1. My u looks a little bit like an uncommitted 9 or a very rounded 4. That looks a little bit more u-like. And so when I do du, I get that du is equal to secant squared theta d theta. And now this is the first time that we really haven't had anything else that gets replaced. So now I got to figure out, okay, tangent is u. So either I can go through and I can plug it in like we've done in the past. I'm going to kind of block this section off. Or you can use the triangle and figure out, okay, what is this square root of 1 plus u squared equal to? Either way, you'll get to the same result. It's just a matter of what are you more comfortable with. So for this one, since we don't have to do like really anything else for plugging in, I'm just going to plug in the tangent part. Now, I'm not going to change these bounds. U equals 4/3 and u equals 3/4. The reason for that is if I do tangent of 4/3, or if I do where does tangent theta equal 4/3, then I'm getting into some very messy decimals, and I would prefer to leave these exact. And if I have to round later on, so be it. But for now, I'd like to avoid it if possible. So this is going to become, so 1 over square root of 1 plus tangent squared theta and that's cubed. And then times secant squared theta d theta. And so 1 plus tangent squared is secant squared. So this is equal to u to the 4th. U equals 4/3 and 3/4 for the bounds. Secant squared theta d theta over, so it would be the square root of secant squared, and then which is just secant squared, and then cube it. So I get secant cubed theta, and that will leave u equals 3/4, u equals 4/3. That just leaves the antiderivative of secant theta d theta. Whoops. Not secant theta. Sorry, I put secant theta. I would like to keep this consistent. There we go. Should be 1 over secant theta, which then 1 u equals 3/4. And again, keeping with the u's just for that. But so if cosine, or sorry, spoiler, if secant is 1 over cosine, that means 1 over secant is equal to cosine. So then what I can do here is I can just say, well, this is equal to cosine of theta d theta, which I know that antiderivative relatively easily. So this is sine of theta evaluated from u equals 3/4 to u. God, that one was just a 4. to u equals 4/3. And again, I need to get it back in terms of my u's. So sine is going to be opposite over hypotenuse. So really what I'm evaluating is the opposite, which is u, divided by the square root of 1 plus u squared, evaluated from 3/4 to 4/3. There we go. So this is 4/3 over the square root of 1 plus 4/3 squared minus 3/4 over the square root of 1 plus 3/4 all squared, which, if I do that, so 4/3 square root of 1 plus 4/3 squared. This is equal to 4/5 minus 3/5. So the final answer is the area between ln of 3/4 and ln of 4/3 of e to the t over 1 plus e to the 2t all to the 3/2 is 1/5. A lot of work and a lot of stuff that doesn't look like it's going to naturally come out to some kind number, but after all the algebra and arithmetic is done, this is just 1/5. So, but anyway, that's the example. So